Hello, I am Frits de Mul and I would like to introduce you to the electric field of a dipole. This presentation is part of a series of presentations about various topics of the electromagnetism. The electric field of a dipole. Given is an electric dipole situated in O with the dipole moment P. Dipole moment P means we have a plus charge and a minus charge separated with a certain distance. And the question is, calculate the E field in arbitrary points P out around the dipole. First we have to do the analysis and look for symmetries, then find an approach to the solution, do the calculations, draw conclusions, and then calculate some field lines in the XY plane. Here is the dipole and point P. We take coordinate axis. The y-axis we take as the dipolar axis, and the symmetry will be cylindrical around that y-axis. We define cylindrical coordinates r, ER, E theta, from the angle theta here, and E phi, and that's the angle phi here. All points at equal r and theta are equivalent. All points at equal r and theta means on the edge of the circle, even if they are at different phi's. Well, we have several approaches possible. We can calculate E with Coulomb and E from the potential with minus the gradient of phi. But we take option 2. And necessary is to calculate the potential first. We calculate the potential here. Suppose we have a dipole is charge times distance, as seen here. That's the dipole moment, and the contributions to the potential from plus q and minus q is Vp is plus q over 4 pi epsilon naught r plus minus q over 4 pi epsilon naught r minus, and r plus and r minus are given here. And this can be written as q over 4 pi epsilon naught times r plus minus r minus divided by r plus r minus. Now, if A is much smaller than r plus r minus, then we can consider the r plus and r minus to be parallel, and the difference between both those two is this distance here, and the distance can be written as A times cosine theta. And so we end up with the potential as a function of r and theta in this approximation is q over 4 pi epsilon naught times A cosine theta over r squared. R squared is r plus times r minus in this approximation. This is called the far field approximation. Well, here is that expression again, and as you can see, P times cosine theta can be written as the vector P, the dipole moment vector, times ER, and ER is the vector pointing from the dipole to point P, where we would like to know the field. And this approximation is called the far field approximation. Now the calculation of E. We use the gradient of the potential, and the gradient is minus dv dx times Ex, and a similar y contribution and a similar z contribution. In general, E is minus dv ds, the coordinate in the u direction, times the unit vector in the u direction, the derivative in the S direction times the unit vector in the S in the V direction times the unit vector in the V direction, and here in the W direction times the unit vector in the double direction. And SU, SV and SW are line elements. For instance, U and V and W could be X, Y and Z, or R, theta, phi. Here U is R, V is theta, W is phi. This is dSU is dr. And this means that V as a function of r and theta is p cosine theta over 4 pi epsilon naught r squared. So ER is dV minus dV dr of ER is 2 pi cosine theta divided by 4 pi epsilon naught r to the third. dV dr. Now the differentiation to theta. ds v, the line element along the v direction, is r d theta. And r d theta is this line element here. In the v direction or in the theta direction is r d theta. And thus Vr theta is p cosine theta over 4 pi epsilon naught r squared, leads to the E theta, the component in the E direction is minus dV over r d theta. E theta is p sine theta over 4 pi epsilon naught r to the third, E theta. So there is a contribution to E along E theta as well. Now the third one, the phi. And here we have the line element along the phi direction, W, and this is, as you can see, r sine theta, that's this line here, r sine theta, times d phi. D phi is here. This is r sine theta. Here, r sine theta, d phi. And this means that with the expression for V, the E phi is dV over r sine theta d phi. E phi is 0. Because dV d phi is 0. There is no phi in the V expression, so it is 0. And then we end up with the expression for ER and E theta, and E phi is 0. ER, E theta, E phi. And this is the total E, and the total E will be in the plane of ER and E theta. Conclusions. This is the V as a function of r and theta. We can write it as a scalar vector product of P and ER. P is the dipole moment vector. The electrical field strength is P over 4 pi epsilon naught to r to the power 3 times 2 cosine theta ER, the ER component, this one, plus sine theta E theta, the theta component, this one. Now let's investigate the directions of E in the 4 quadrants. Here is the expression with the cosine and the sine. And here are the 4 points of P in the 4 quadrants. This is the P we had met already before with an ER and an E theta in these directions. ER along the R, E theta along the theta. Here they are in these directions, here in these directions, and here in this way. And in quadrant 1, the two functions cosine and sine are positive. In 2 is the cosine and negative, like in 3, and the sine is negative in 3 and 4. And this means that for the ER and E theta components it will be these contributions, and here these contributions, because the cosine is negative but the sine is positive. Here we have both contributions are negative, cosine and sine, and here is the sine negative. So this is the total E, and the total E is in this direction, and here the same, and we have a mirror line here along the dipole moment vector, and this is the total field here. Along the dipole moment vector the lines are in this way because the cosine is 1 and the sine is 0, so there is only an ER component, and here as well there's only an ER component. Here for theta is 90 degrees. The cosine is 0 but the sine is 1, and thus we have a contribution along the sine, along the theta direction, and here as well. So here are the field lines in the xy plane. It's given by the y dx is ey over ex. And then we can calculate the direction of the field lines in between minus q and plus q. This is not in far field approximation, of course. For a is 20, and the distance a is the parameter between q minus q and plus q. When we decrease the distance, the field looks like this. Again, the field looks like this, and here a is 1/10. And this is the far field approximation. Altogether, here we have a is 20, a is 10, a is 1, a is 1/10, and this is the far field approximation. And this is the end of the presentation. Thank you very much.